Here is example 5. Given the function, determine the symmetry of the graph. And then we're going to answer parts B to E, which are very similar to example 4. When we mention symmetry of a graph, we are really referring to whether the graph is an odd function that has a rotational symmetry or an even function which has line symmetry. If you recall the definition of these types of symmetry or these types of functions, an odd function has rotational symmetry, meaning that negative of f of negative x is equal to f of x. And then if a function is even, then we have f of negative x equal to f of x. So let's apply this to our function here. Part A. I'm going to first work out f of negative x, which gives me e to the power of negative x to the power of 2 over 2, which looks like e to the power of negative x squared over 2. It turns out this is f of x, and we have an even function, which implies that there is line symmetry in this function. Question B and C, when we deal with increasing, decreasing function and extreme values, we are considering f prime of x, the first derivative. Let's take the first derivative of this function. We have e to the power of negative x squared over 2 multiplied by the derivative of this whole exponent, which means that we have negative 2x over 2 that simplifies into negative x. Now, in order to find the extreme value, we'll set f prime of x equals to 0. This implies that either negative x is equal to 0 or x is equal to 0, or e to the power of negative x squared over 2 is equal to 0, but this has no solution because an exponential function has a horizontal asymptote along the x-axis. Okay, so we got a key point here for sure, x equals to 0. Let's use this information and test points to see when does this function increase or decrease and what type of extreme values we have. I'm just going to have a number line ready. And on this number line, I'm going to mark 0. That's my key point here. Let's check. Let's say I'm going to evaluate f prime at f of negative 1. What does that give me? I have positive 1 times e to the power of negative 1 over 2. That means x is increasing during this interval because e to the power of negative 1/2 is still a positive number. Let's use f prime of 1 to test out the sign of the first derivative when x is greater than 0. This gives me negative 1 e to the power of negative 1 over 2. This actually gives me a negative value, meaning that the function is decreasing in the interval of x is greater than 0. So let me highlight these as my answers. So if I make a sketch like that, there is a maximum in this interval at f of 0. Let's figure out the y coordinate of that. We have f of 0 equals to e to the power of 0 squared over 2, which is 1, meaning that there is a maximum at 0, 1. Okay, so let's highlight this. That's part B and C together. Part D of the question asks for concavity of the graph. So now we need to take the second derivative, f double prime of x. We have a product. We're referring to this line here. So let's go. Negative x turns into negative 1, e to the power of negative x squared over 2, plus, then I have to take the derivative of e to the power of negative x squared over 2, which is e to the power of negative x squared over 2 times negative 2x over 2 multiplied by negative x. Sorry, it's a little messy. Let's reduce. Okay, all of those are gone. I will factor out e to the power of negative x squared over 2 so that I will have negative 1 plus x squared, which technically is x squared minus 1. That will allow me to factor the difference of squares, x plus 1, x minus 1. We already know that the e to the power of negative x squared over 2 has no solution. In this case, if I set f double prime to 0, meaning that x is either negative 1 or x is positive 1. Okay? Now let's check the sign of f double prime, the second derivative, so that we can confirm the concavity of this particular function. Negative 1, positive 1. Let's test out f double prime. Pick a number, say f double prime of negative 2. I have 4 minus 1, 3, and then that's positive, this is positive. Okay, and then let's pick, say, can I pick 0? I think so. And if I pick 0, I get negative. And if I pick positive 2, works out to a positive. Very well. It means that this function concave up when x is less than negative 1 or x is greater than 1. It concaves down when it is between negative 1 and 1. Let's figure out the points of inflection. I need the value of f of negative 1, which is e to the power of negative 1, or negative 1. So many negatives. This is e to the power of negative 1/2. And f of positive 1 is e to the power of negative 1 squared over 2. Also the same thing. So the 2 points of inflections are negative 1 e to the power of negative 1/2, and also 1 and e to the power of negative 1 over 2. Now let's make a sketch of this graph here. I need a set of axes. Okay, good enough. They're just roughly, okay, these are just rough sketch. I know that there is a max, not local, it's global actually, at 0. It's not drawing. Hello. Okay. 0 and 1. I have a maximum. At negative 1 and 1, at the same level, I've got my points of inflection. So roughly, it's going to look something like this. And here is question